Hello everyone, we are Team Zebra and our project is Printer Real-Time Torque Measurement. Our team's technical director is Matthew Corbis, a URI alumni who graduated with a Master's of Science in Mechanical Engineering and is a part of class of 2016. Our team is comprised of myself, Chris Medeiros, and my two teammates, Moboy Da and Jose Valdez. I am the team's computer engineer and will be a part of class of 2021, and Jose and Moboy are both electrical engineers who will also graduate in 2021. Zebra is located in Lincoln, Rhode Island, although they have many other locations all over the world. They were established as a company in 1969. They are known as the market leader in mobile printing technology, as well as being industry leaders in segments such as barcode scanning and specialty printing. The motivation for this project can be broken down into two sections, the first being correcting the printer media sticking issue. Zebra runs into an issue where certain media will stick to the print head while printing, which is caused by the heating of the media through the print head. We plan to be able to gather torque data of the motor via a torque transducer to observe these issues and take proper action to correct this problem. Secondly, since our design is based on a past fixture design, we plan to improve upon this design by interfacing all peripherals to one device. We will have a custom PCB manufactured to perform all functions that would previously have been performed through multiple devices. Our anticipated best outcomes would be ease of test as well as reliable data collection. We are designing our system to have a user-friendly interface and faster troubleshooting capabilities. This will in turn reduce testing and troubleshooting time for Zebra technicians and making the process more economically efficient. Data collection will also be improved as printing conditions will be more accurate and printing quality will improve overall. This will improve customer satisfaction as well as Zebra's ability to address customer complaints, generating more economic growth for the company. This is our setup one block diagram. Our microcontroller will call to send a label to the printer to initiate the printing process. Our custom PCB will accept the motor step output and run a new hybrid motor at the desired step rate. A torque transducer and data acquisition unit will record the torque data and send it to the microcontroller for analysis. This is our setup 2 block diagram. The microcontroller will send a step signal to our custom PCB to control a bipolar stepper motor. A magnetic particle brake will be applied as a load. All torque data that is collected through the transducer will be input into a data acquisition unit and output back to the microcontroller. This is the proposed layout of our custom motor controller PCB. It will have a voltage boost and current control, as well as a section for temperature reading and motor waveform capture. There will be a section for data I/O, as well as multiple motor drivers implemented in a generic motor driver interface for future inputs. Our team's accomplishments this semester include the hybrid motor's pulses per second conversion calculation, integrated circuit selections, and a prototype design. One of the major tasks of this project is to take a Zebra printer's motor driver inputs and sync that speed to a new hybrid stepper motor. A big step in getting there is calculating how to match those step signals up so they essentially perform the same task. This hybrid stepper motor will be a replacement to the typical motors that Zebra uses in their printers. Team Zebra implemented this calculation in an Excel sheet, which essentially simulates what the microcontroller will do later on. The user will input 5 conditions: full steps per line, platen diameter in millimeters, microstepping resolution of the printer, speed in inches per second, and dots per inch. Using these parameters, we implemented functions that calculate the hybrid motor's PPS rate, as well as the accuracy of the calculation. In order to drive our hybrid stepper motor, we needed to select a motor driver IC that would be fit for our application. We were looking for an IC that handled at least 20 volts with a 2 amp drive current, as well as one that supported up to 256 microstepping resolution and a step direction interface for ease of implementation. The IC that we selected is Texas Instruments DRV8424, which was one of the only ICs that fit all of the prerequisites for our design. Upon selection of our IC, we designed a motor driver daughter board for our custom motor controller PCB. Using Circuit Maker as our software, we had to implement the component footprint and symbol ourselves, as it was not available through the Octopart libraries. We used the datasheets, dimensions, and specifications to create a custom footprint as well as a custom symbol for our daughter board. As a computer engineer, I plan to have a major role in the front-end and back-end software development for our system. On the back end, we need to implement the software that will run the system. We are using an STM32 microcontroller board, which uses C or C++ as the main programming language. The software will need to be able to take the printer's motor driver signals as inputs and output the correct PPS rate to run the hybrid stepper motor. These parameters will be set by the graphical user interface. Our microcontroller board comes equipped with an Ethernet port, and we plan to implement the graphical user interface over the internet using a web server. The user will input the 5 conditions required for calculations, and the system will respond appropriately based on what the user requested. The next speaker will be Moboy, one of the 2 electrical engineers on Team Zebra.
To reintroduce myself, my name is Moboy Dier, and I am one of the 2 electrical engineers. What's highlighted in the layout is what I will be talking about. In addition to what we have accomplished are motor voltage boost device and component to control voltage. Due to the project's requirement of willingness to vary the voltage that will be fed into the stepper motor driver, the buck converter is such a device that does it all. It can vary the voltage by its voltage divider components. In this slide, I am briefly showing you where we will implement the digital potentiometer and the reason for its choice. So if you refer to the diagram to the right corner, the voltage divider resistors, when they kept fixed, the output voltage of the buck converter remains fixed, but the project has required us to change that voltage. So what we would like to do is have a varying resistor. So the digital potentiometer fits perfectly into that role. With the project running along as we had hoped for what we like to accomplish in the future is switching up the hybrid motor with a bipolar stepper motor and test it. Also, have a magnetic particle brake that can slow down the torque whenever needed. Implement a thermocouple right above the motor that will be tested to record the temperature so that we could keep an eye on the motor and not damage it. Up next is the other electrical engineer, Jose Valdez.
My name is Jose, and I'll talk about our prototype, selected current control unit, and microcontroller. We have designed a prototype which consists of 4 evaluation boards to test components' operability, voltage, and current. Once these are tested and verified to be working at the desired parameters, we'll implement the current and voltage boost control ICs to our custom motor controller board PCB design. Our selected TI-DRV8424 motor driver integrated circuit chip also serves as the current control unit. The voltage sent to its voltage reference VREF pin will be used to scale the current delivered to the motor. And we will design a delicate circuit that will allow to capture and analyze a waveform from this delivered current. Our selected microcontroller unit, the STM32F767ZI, has a powerful 32-bit architecture with embedded debugger and programmer. It will interface the entire system at high performance speeds, which will be adequate for the high hybrid PPS microstepping signal. It is worth mentioning that this STM32 board comes with an Ethernet connector which will allow program code to be downloaded to the microcontroller from a web platform. The flow of signals as well as mechanical connections can be seen on the picture shown. As an electrical engineer, I plan to append and properly route all components and peripheral signals on the fixture board PCB designed. I will also help on the software and debugging processes. Our future accomplishments will be the following. Develop software for the microcontroller to run and interface the system. Implement selected ICs to custom PCB design. And implement particle brake as well as the thermocouple to realize setup 2. We would like to acknowledge our technical director, Matthew Corvise, our program director, Professor Sunak, and give special thanks to our dear Joe, Patrick Hergerty, Zebra Electrical Engineer staff member, our coordinator, Alex DePetrillo, and our PCB design professor, Mike Smith. Thank you all for your continued support.